So I wanted to talk about the last part of experiment number 9. And I wanted to bring this up because of the fact that you're looking at older data, the data that you collected last week, and you might be curious, how do I navigate this? How do I solve these sorts of problems? Well, that's what we're going to work on real quick. Okay, so one of the things that you have to solve for at the end of experiment number 9 is you have to solve for your delta H Rxn per mole for 3 different reactions. Well, we've got NaOH solid going into solution and making an NaOH aqueous. Okay. Second, you've got NaOH aqueous plus HCl aqueous yields NaCl aqueous plus H2O as a liquid. And you got to solve for the delta H Rxn per mole there. And then finally, we've got reaction number 3, which is intended to be a combination of those two. We've got NaOH solid plus HCl aqueous yields NaCl aqueous plus H2O. And again, you've got delta H Rxn per mole from that. Okay, so the way that I'm going to approach this is I'm going to look back at my experiment number 8 data, and I'm going to use that to show you how to calculate this. Okay, so reaction number 1, NaOH going into solution. Okay, so what is our heat of reaction here? Our delta H Rxn per mole. What we need to do is, one thing that we know is we know that this is an exothermic reaction, therefore this value is going to be negative. So what I have is, I have a couple of things. I have my initial temperature of water. I have my final. And therefore I have my change. And what I'm going to do is I'm just going to use some hypothetical values. You'll have to plug in your own values for this. But we're going to use the equation Q equals mc delta T. Okay, so this M right here, this is the mass of the water that we actually monitored and saw the temperature change. That was 50 milliliters with a density of 1 gram per milliliter. So 50 times 1 G per ml equals 50 grams. Okay, so I'm going to set this up. Q equals 50 times. Now, this next part is my standard enthalpy, or sorry, is my heat capacity, 4.184 joules per gram degrees Celsius. So 4.184 joules per gram degrees Celsius. The last is my temperature change. So that's where my initial temperature and my final temperature comes into play. So let's say hypothetically that my initial temperature was 20.6 degrees Celsius. And my final temperature was 29.3 degrees Celsius. Well, that means my water, my 50 grams of water went up 8.7 degrees Celsius. So my delta T is 8.7. I know that this is going to be a negative value, but all that I need to do is take my calculator and say 50 times 4.184 times 8.7, and I get negative 1820.04. But I need to convert that from joules to kilojoules. And how do I do that? Well, I move my decimal point to make this negative 1.82004. Okay, Now, what I just solved for there was my delta H of my reaction. But now I need to put it in terms of moles. Well, what are the moles that I'm going to use? I'm going to use the moles of my sodium hydroxide. And so to do that, what I'm going to do is figure out, well, I had 2 grams of sodium hydroxide. And what is my molar mass of sodium hydroxide? My molar mass of sodium hydroxide is 40. So 2 divided by 40 is 0.05 moles. So I'll take this number right here and divide it by 0.05 moles. And that's going to ultimately give me, where's my calculator? Negative 36.4, that's a 4, 0 kilojoules per mole. Okay, so that's my first value. So that's looking at reaction number 1 right here. Reaction number 2 was where I had HCl plus NaOH, and I produced NaCl aqueous plus H2O liquid. So what I did was I got 25 milliliters of a 0.4 molar HCl solution and 25 milliliters of a 0.4 molar NaOH solution. Now, what I'm concerned with ultimately is, again, the values that plug in here. Q equals MC delta T. I saw a temperature increase. So let's say that, well, let's look at our first thing, mass. What is the mass? Well, it's the mass of the 2 solutions combined, which was, again, 50 milliliters total. So I'm going to say 50 grams is the mass of my solution. Heat capacity, again, 4.184 joules per gram degrees Celsius. Delta T, well, delta T, that's my initial temperature and my final temperature. Let's say, hypothetically, my final temperature was, let's say it was 26 degrees Celsius, and my initial was 21.2 degrees Celsius. My delta T here was, well, be 4.8 degrees Celsius. So plug all those values in. 50 times 4.184 times 4.8. And I get, again, a negative value, negative 1008.16 joules. I'm going to divide this by, well, what do I divide it by? I divide it by the number of moles of my limiting reactant. Well, I did equal concentrations, or sorry, equal volumes of equal concentrations. So I had, that would be my volume, which is 0.025 times 0.4, my concentration, and I would get a value of 0.01 moles. So I'm going to plug this in. I'm also going to convert this to 1.008 kilojoules. So 0.01, and I get 100.816. This is still a negative value, kilojoules per mole. Okay, so now I have values for this one. I have a value for this one. You also have data, you would calculate this the exact same way for this one. Now, Hess's law says that these 2 values right here, they should combine to basically produce this overall reaction. And if we look at our first two reactions and draw our line here, I'm going to say that this value is negative, what did I get? Negative 36.4 full mole. Okay, and then this value is just a second. Negative 100.816. These two reactions, well, I should be able to cancel everything out and come up with this overall reaction. So I'm going to underline the things that are common in reaction 1 and reaction 3. Sodium hydroxide as a solid is a reactant. It's both in 1 and 3. Sodium hydroxide aqueous, is that present in my overall reaction? It's not. It's instead present in reaction number 2. So this and this will cancel out. HCl as an aqueous solution is present in reaction 2 and my overall reaction. NaCl is present in my as a product in reaction 2, and it should be present, and it is present as a product in my overall reaction. H2O is a liquid. Well, I forgot to write liquid there, but it's there also. So essentially, what this means is my expectation from Hess's law is that this, well, I'm going to do the Hess's law calculation, which tells me that this should be negative 137.216 kilojoules per mole. Now, what does that tell me? That tells me that whenever I solve for this, I'm expecting it to be about that. Is it absolutely going to be that? No, maybe it's not. What does that tell you? That tells you that maybe one of your reactants was, or maybe you didn't add enough of your reactant, or maybe you didn't measure things properly. Something might have gone wrong along those lines, but it's probably going to be approximately that. All right, well, I hope that was helpful in showing you how to work through the experiment number 9 data, or sorry, experiment number 8 data for the calculations for experiment number 9. And I hope that gives you a better illustration of Hess's law. All right, well, have a good one.